Okay, now it's time to put it all together. Example 7, find all the roots of the polynomial k of x equals 2x to the fourth minus 5x cubed plus 20x squared minus 45x plus 18. Now, uh, in my other window, I have that step by step listed to help me out, to refer back to it to make sure I'm going through and doing all of the things. First step, write your polynomial on the page. I got lucky, it's already on my page. Step 2, identify the number of roots of the polynomial using degree. I see this is a fourth degree polynomial, so I should expect in my solution there to be 4 roots. I'm looking for 4 values of x that make this polynomial 0. That's what it means to be a root, if you forgot. Step 3, determine the possible rational roots. This is rational zero theorem. I take my constant term, 18, and look at all of its factors, 9, 6, 3, 2, and 1. And look at all of its, the leading coefficients terms. And that's a 2 there, so we got 2 and 1. And now I start listing them all out. 18 divided by 1 is 18. 18 divided by 2 is 9. 9 divided by 1 is already there. 9 divided by 2 is 9 halves. So I like separating out the fraction ones. 6 divided by 1 is 6. 6 divided by 2 is 3. 3 divided by 1 is 3. We already got it. Divided by 2 is 3 halves. 2 divided by 1 is 2. 2 divided by 2 is 1. And 1 divided by 2 is 1 half. And of course, there's the positive and negative version of each one of these. All right, so there is my rational zero theorem. I've narrowed down the infinite number of choices to 1, 2, 3, 4, 5, 6, 7, 8, 9 times 2, 18 possible rational zeros. A lot better to check 18 numbers than it is to check all of them. So, step 4, determine the number of positive, negative, and complex roots. So, I'll do this one with green here. I check my sign changes. This is for the positives. Positive to negative, negative to positive. Positive to negative, negative to positive. That is 4 sign changes, so I could have 4, 2, or 0 positive roots. Now, I need to have k of negative x, so I'm going to write that on the side here. And if you remember, the tip was, if it's an even exponent, keep it the same. If it's an odd exponent, change its signs. So I only have to do work in half the spots, which is kind of nice. It's a negative 45x, so that turns into a plus 45x plus 18. And now I check these signs here, and you can see we have positive, 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 positive. There's no sign changes at all, which tells me for the negative solutions there are 0, which is kind of nice. From this list where it was all, I said there was 18 possibilities because of plus or negative, positive or minus, no negatives. I just cut all those in half. Nice. And the last one, of course, would be the complex numbers. If I have 4 positive roots, I have 0 complex roots. If I have 2 positives, I should have 2 complex, because that needs to be a total of 4. And if I have 0 positives, then I should have 4 complex. If I have 4 complex roots, that's going to be very tough to solve. I don't know if there's a good way of doing that other than getting lucky with a factor by grouping. All right. So we've done our preparation. We've got all the possible rationals. And we've already eliminated half of them by using Descartes' rule of signs. So I'm going to start guessing and checking with some synthetic substitution. And I'm not going to make this hard on me. I'm not going to start with 18. I'm going to start with 1. 1. And then I set it up 2, -5, was that 20, -45, and 18. Drop it down, we got ourselves a 2, 2, add them up, multiply it, add them up, multiply it, add them up, multiply it, and we get -10. So 1 is not a root. We also know -1 isn't a root because there's no negatives. So cross that off our list. 1 down, a bunch more to go. 2. And we've got 2, -5, 20, -45, 18. You can see why I made such a point of synthetic division is really important because we're going to do it a bunch later. On this problem, we're going to do it 4, 5, maybe 6 times. Who knows? Let's see here. All right. Drop it down, multiply it out, add them up, multiply it out, add them up, multiply it out, add them up, multiply it out, and look at that. We found our first root. That's a root. So, of our roots, 2 is our first value, and it's a positive number, right? Which means I'm expecting now to at least have 2 positive roots, maybe 4 positive roots, not 0. I found 1, so I've already got more than that. So that's my scenario. I'm either going to have 2 or 4 now. And of course, this is my depressed polynomial. It's a 3rd degree polynomial now instead of a 4th degree, so I have less things to do. So my next one I'm going to try, let's try 3 from the list. I guess on my list I should mark off that 2 worked, so I'm going to give that a little circle there with the plus sign circled. It's positive 2. All right. I'm going to try this out with 3, but this time I'm going to use that depressed polynomial. 2, -1, 18, -9. It makes my life easier. Synthetic substitution got easier. Part of the reason why we can do this is if it was a factor of the original, it will be a factor of the depressed as well. So it makes our life a little bit easier. Drop it down, 2, multiply it out, add it up, multiply it out. Oh, why did I write -5 there? That should be +5. Multiply it out, add it up, and you can see here this is not looking very good for 3 as a possible root. 99, so there the remainder is 90. Okay, so not a root. Go back to my list, cross it off. Now, I could try 6, 9, and 18, but my bet is they're just going to get even bigger, right? Because I know for a 3rd degree polynomial, as x increases, if it's got a positive leading coefficient, as x increases, the function goes to positive infinity. Let's try one of the smaller numbers there. Let's try 1/2. You go, oh, Willig, I thought we were going to get away without having to use any of those fraction ones as our possible solutions. And, well, you thought wrong. Sometimes you got to use them. Sometimes the only rational ones you get are one of the fraction ones. All right, but the process is the same. Drop down the 2, multiply it by 1/2. Add them up, multiply it by 1/2. Add them up, multiply it by 1/2. And look at that, we've got ourselves another root. There's a root. All right. Okay, so now I can add 1/2 to my list of roots above. And now you can see I was right. I said there was at least going to be 2 roots in there. I just found the other one. So let's go ahead and give that guy a circle right there and the positive. All right, now I could keep doing synthetic substitution, and I could keep doing it with this leftover polynomial. But what you might see here is, or might be able to recognize, this is another depressed polynomial. And you see how there's only 3 terms there? That means it's a quadratic. 2x squared plus 0x plus 18 equals 0. Now this is something I can actually solve. I'm going to drop the 0x there. I got 2x squared plus 18 equals 0. Let's factor out the 2. X squared plus 9 equals 0. Well, I know 2 can't be 0. There's no variable there. So all I've got, well, I could divide both sides by 2, right? This is what I've got now. I've got x squared plus 9 equals 0. Well, I know how to take the square root of stuff. And I get x squared equals negative 9. Take the positive negative square root of both sides. And I'm taking the square root of a negative, so x equals plus or minus 3i. And guess what? Look back up here. Plus or minus 3i. There are 4 solutions right there. 2 of them were positive, 2 of them were complex. Now, a note here on this part of the solving process. This is step 5, part C. Another possible thing that could have happened here is I could have had this quadratic be something that I can't factor or take the square root of simply. So quadratic formula is a pretty common option here. If you don't remember it, I mean, you should remember it. But I mean, I remember it pretty easy because I'm always writing it down. You should always be writing it down too. So you're going to use a quadratic formula there, or factoring. Or what we did here, or just using the square root. Once you get it down to the quadratic, one of those 3 things are going to be your option, and that's going to be the best way for you to find the last 2 solutions. Anyways, that's how you put it all together. Let's double check. We got our 4 solutions. 1, 2, 3, 4. 2 positives, 2 complex, 0 negatives. There they are. Those are the 4 numbers that make this polynomial equal to 0.